In this lecture, we solve an LPP by simplex method with a variable is unrestricted in sign. Okay, that is when the variable of an LPP is in unrestricted sign, then we are going to discuss how to solve this type of LPP by simplex method. Okay, and we know that when we solve an LPP by simplex method, we must transfer it in standard form. Okay, and to make it standard form, all the variables must be of greater equal to type. So we first try to change the unrestricted variable into greater equal to sign. And how can do it? Here we put, if the variable x3 is unrestricted, we put x3 dash, x3, this is equal to x3 dash minus x3 double dash. Then we can write x3 dash and x3 double dash may be greater equal to 0. Okay, because the difference of two positive number may be positive or may be negative or may be 0. That is unrestricted in sign. So we replace x3 in the problem by x3 dash minus x3 double dash, and we get the LPP becomes max z. This is equal to 5x1 minus 2x2 plus x3 dash minus x3 double dash. Okay, here we put x3 dash minus x3 double dash in place of x3, and all the x3 is replaced by x3 dash minus x3 double dash, and we get the LPP becomes this, right? Now here two constants are given. The first constant is of less equal to type and the second constant is of greater equal to type. So we must have to introduce an slack variable. Let the slack variable is x4 and surplus variable, this is named as x5. Okay, to make the less equal to and greater equal to into equal to type. Okay, and since there be only two equations, so we must have to get the standard basis in two dimensions. That is, one is 1 0 and other is 0 1. Okay, and when we put slack variable x4 in the first constant, then obviously we get the first standard basis, that is of the form 1 0. But to get the second basis of the standard basis, that is 0 1, we must have to introduce an artificial variable. Okay, and this is named as x6. So we introduce a slack variable x4 in the first constant and a surplus variable x5 and artificial variable x6 in the second constant. Okay, and since here we introduce an artificial variable, so this method is known as big M method or artificial variable method or Charnes M method or method of penalty, right? And the LPP in standard form we write as max z. This is equal to 5x1 minus 2x2 plus x3 dash minus x3 double dash. We introduce the slack and surplus variable with the objective function with 0 coefficient, that is 0x4 plus 0x5, but the artificial variable with the coefficient minus m. This is minus m into x6, and m is very large or big. In this reason, this is known as big M method. Okay, and this is big M method. We write here big M method. Okay, and the constants are written as 2x1 plus 4x2 plus x3 dash minus x3 double dash plus x4 plus 0x5 plus 0x6. This is equal to 6, and the second constant is 2x1 plus x2 plus 3x3 dash minus 3x3 double dash plus 0x4 minus x5, because this is surplus variable, plus x6. This is equal to 2. This is artificial, this is surplus, and this is slack. With x1, x2, x3 dash, x3 double dash, x4, x5, x6, all are equal to 0. Now we draw the simplex table. What is simplex table? We draw the simplex table as, this is the simplex table. We write here, this is first simplex table. Okay, first simplex table, and the table is of the column like this. This is the table, and here we draw 3 columns. Okay, and there are the vectors a1, a2, a3 dash, a3 double dash, a4, a5, a6. Okay, what are a1, a2, a3, a4, a5, a6? These are the column 2 to the first column, second column, third column, fourth column, fifth column, and so on. Okay, we write this column as 2, 2. This is 4, 2. These are 1, 3, 1, 3. These are minus 1, minus 3, and the a4 vector is 1, 0, a5 vector is 0, minus 1, and a6 vector is 0, 1. Right? This is the table, and here we draw another 2 column here. The first column is, we write here mean ratio, and in the last column we write upper cell. Okay, and other cells are like, this is B and this is CJ. Okay, what is B? B is 6, 2. This vector. This is 6. This is 2. And CJ are given by the cost vector. These are 5, minus 2, 1, minus 1, minus 2, 1, minus 1, and 0, 0, minus m, 0, 0, minus m. Okay, and now we fill up the remaining column. This is XB, this is B, this is CB. What is the meaning of B? B with the basis vector. What are the basis vector? The A4 and A6 are the basis vector, because 1, 0, this is A4, and 0, 1, this is A6. These two are basis vector. We write here A4 and A6. We must write the first vector, that is 1, 0 in the first row, and the second vector, that is 0, 1 in the second row. Okay, A4, A6, and we write here corresponding basis variable. These are x4 and x6, and this is given by the cost vector corresponding to the basis. The cost vector corresponding to the basis are A4, this is 0, and A6, this is minus m. This is 0, this is minus m. And we write here Zj minus Cj. Okay. Now we calculate all the net evaluation. These are the net evaluation. How to calculate net evaluation? We find Zj, this is given by CBI into AI. How to find? We give an example for calculating Z1 minus C1. We calculate CB1 into A1. We write this is not CB1, this is CB only. So CB into A1. This means CB means 0 minus M dot A1. A1 means 2, 2. This 2 vector and this is a dot product. So this is 0 into 2 minus M into 2. So this is minus 2M. Now Zj minus Cj, that is C1. Here C1 is 5, right? Cj means C1, C2, C3, C4 and so on. So we get this is minus 2M minus 5. And similarly for the second column, this is minus 2M, this is minus 2M plus 0 plus 2, this is minus 3M minus 1, and this is 3M plus 1, this is 0, this is M, and this is 0. Okay, and we make a small correction here. We write here 1 because the coefficient of x2 is 1. We wrongly write it, it is 2 previously. Okay, now we have to find out the most negative net evaluation. What is the most negative net evaluation? Already we says here M is big, that is M is a big real number. So minus 3M is the most negative from this all Zj minus Cj, and since this is the most negative, this indicates that this vector is the incoming vector. Okay, and this is said to be incoming vector. Okay, or it is also said to be entering vector. Okay, incoming vector and or entering vector. Now we have to find the mean ratio. What is the mean ratio? The mean ratio is given by B, this vector by this vector. How to find it? This is as 6 by 1 and this is 2 by 3. Okay, 6 by 1 and 2 by 3. We divide all the element of B vector with the corresponding element of entire vector. This is the mean ratio, and clearly this is 6 and this is 2 by 3, so this is minimum. Okay, we have to find the minimum ratio, and in this reason this is said to be mean ratio. Now the row which mean ratio occurs, that is in the second row, this is the key row, and the column of entering vector, this is the key column. Okay, and the element on the intersection of key row and key column, that is 3, is said to be key element. We write it is key element. Key element. Okay, and since in this row there is the vector A6, so the vector A6 must leaving the basis, and A6 is the leaving vector. We indicate by an arrow. This is leaving vector, or also it is known as outgoing vector. Okay, these are incoming vector and outgoing vector. Now we go to the second simplex table. We already drawn the second simplex table, and how to fill the second simplex table? The second simplex table, we start from this basis column, B column, that is this is A4 and this is A3 dash, because A3 is incoming and A6 is outgoing. So A3 dash replace the outgoing vector A6, and clearly this is given by x4 and this is x3 dash. And how to write CB? CB is nothing but 0 and A3 dash or A3 dash, this is 1. Okay. Now we have to make the key element 1. How to make the key element 1? By operation, this is the second row R2 dash, this is equal to 1/3 into R2. By this operation we make 3 to 1. Okay. Why it is made to 1? Because if it introduced in the basis, so it must have to the form 0 1, because 0 1 is replaced by A3 dash. Okay. So this is 1 and this is 0. Now we divide all the element of this row by 3 and getting the result as 2/3. This is the first element. This is also 2/3. This is 1/3. This is 1. This is -1. This is 0 and this is -1/3 and this is 1/3. Okay. This is the second row. Now we have to make this is 0. How to make it 0? This is the new second row and we operate as R1 dash. This is equal to R1 minus R2. What is R2? Or we can write this is R2 dash. R1 dash, this is equal to R1 minus R2 dash. This is the new R2, that is R2 dash, and R1 means old R1. Now this is given by 6 minus 2/3. This is 18 minus 2/3. So it is 16/3. We write here 16/3. And this element is 2 minus 2/3. And this is 4/3. And this is 4 minus 1/3. This is 11/3. Okay. And clearly 1 minus 1, this is 0, and this is -1 minus 1, this is 0, and this is 1 minus 0, this is 1. This is given by 0 minus of -1/3, this is 1/3. Okay. And this is 0 minus 1/3, this is -1/3. Okay. This is the second row and this is the first row, and this is the second simplex table. You can leave this column as empty column because the artificial variable, if once leave the basis, then this artificial variable cannot be incoming vector again. So to save our calculation or time or to reduce our labor, you can leave this column as empty column. Okay, that is, you can not calculate this column and it is remains blank. Okay. Now again we calculate Zj minus Cj as above. The net evaluation for the first column is obviously this is 2/3 into 1 minus 5 and this is minus 13/3. And for the second, this is 1/3 plus 2. This is 7/3, and this is obviously 0, and this is given by 0 also. This is -1 plus 1. This is 0, and this is 1/3. Sorry, this is -1/3, and we get here two negative net evaluation in the first and in the last, and clearly this is the most negative net evaluation. And since -13/3 is the most negative net evaluation, so this is the entire vector. Okay. Now we find out the mean ratio. What are the mean ratio? Mean ratio is given by the first mean ratio is 16/3 by 4/3, and this is equal to 4. And the second mean ratio is obviously 2 by 3 by 2 by 3. This is 1. So this is minimum, right? And since this is minimum, so this is the key row and this is key column, and 2/3 is the key element, right? And since this is the key element, and we clearly say that A3 dash is the outgoing vector. Okay, and now we here symbolize the A3 as the outgoing vector. The basis column of third simplex table. This is third simplex table. What is the basis column? Basis column is A4 and A1, because A1 enter in the basis in place of A3 dash. So here we write A4 and A1, and corresponding the variable x4 and x1. Okay, this is A1, and now this is x4 or A4 means this is given by 0, and A1 this is given by 5, right? This is 5, and here we make operation R2 dash. This is equal to 3 by 2 into R2. R2 dash, this is given by 3 by 2 into R2. This is the old R2 and this is the new R2. Why we make this operation? Because we have to convert it into 1. So we multiply all the element of row by 3 by 2. And 1, this is also 1, and 1 by 3 into 3 by 2, this is given by half, and this element is 3 by 2. Okay, and this is minus 3 by 2, minus 3 by 2, this is given by 0, and this is given by minus half, and this is obviously black as in the previous table. And this operation is given by R1 dash. This is R1, this is the old R1 now, minus this is 1, and also this is 4 by 3. So we make the operation 4 by 3 into R2 dash. Okay, and this is given by 4 by 3 minus 1 into 4 by 3 into R2, this is 0, and this element is 16 by 3. 16 by 3 minus this is 1 into 4 by 3. So obviously this is 12 by 3, that is 4. Okay, this is 4, and by same argument we fill the other element by the same operation as. Again we calculate all the negative evaluation as previous. We get this is 0. This is given by 5 by 2 minus of minus 2. This is 5 by 2 plus 2. So this is 9 by 2. We get this is 9 by 2. And this is 0 into minus 2. This is 0. 5 into this. This is 15 by 2 minus 1. And this gives 13 by 2. This is 13 by 2. And this is given by minus 15 by 2, minus 15 by 2 plus 0 plus 1. Okay, so this is minus 13 by 2. We write here minus 13 by 2. This is obviously 0, and this is minus 5 by 2 minus 0. So this is minus 5 by 2. Right, and the net evaluation corresponding to all the basis vector must be equal to 0. Okay, now we have to find most negative. This is minus 13 by 2 and this is minus 5 by 2. Obviously the most negative is minus 13 by 2. Okay, this is the most negative net evaluation. Now we have to find the mean ratio. Okay, and in this column it is clear that two elements which are 2 and minus 3 by 2. Since this is negative, so here we not divide 1 by negative element. Okay, here we make a line like this. This indicates that we cannot make the division because of this is negative. Okay, So this element cannot be an key element. Negative element or zero element cannot be a key element. And so we make only one division. This is 4 by 2, and obviously this is the minimum, and this is the key row, right? And this is key row and this is key column. So this is the key element, and obviously this element or this vector A4 must outgoing vector, and we symbolize the outgoing vector sign. Okay, now we make the next table. Now in the fourth table we write first the basis vector. What are the basis vector? Here A4 is replaced by A3 double dash. Okay, so we write A3 double dash, and this is remains A1, and obviously CB is given by A3 double dash means -1 and A1 means 5. Okay, and this is X3 double dash and this is X1, and now we make this 2 becomes 1. So make an operation as R1 dash, this is equal to half into R1, and getting all the row as by dividing it by 2. This is 4 by 2, so this is 2, this is 0, this is 3 by 2, this is -1, this is 1, this is half, and this is obviously half. Okay, and this element becomes 0 by operation R2 dash, this is equal to R2 plus, this is minus, so we make plus 3 by 2 into R1, 3 by 2 into R1 dash, and this operation gives this is equal to 0, and we make the same operation for all the element of A1 or all the element of second row. We get this operation, we directly write here all the element of the second row, and by similar argument we calculate all the value of Zj minus Cj. Okay, and clearly the value of Zj minus Cj, these are 0, 57 by 4, 0, 0, 13 by 4 and 3 by 4, and all are greater equal to 0. So we say that the condition of optimality satisfied. Okay, and in this case we find out this cell. What is the value of this cell? This cell is nothing but the dot product of this vector and this vector, and this is given by -2, this is -1 into 2, and this is 5 into 4, and the sum of these two product, so this is 18. Okay, 5 into 2, this is 20, -2, this is 18, and this is the value of the objective function, that is the maximum value of Z, and we reach to the optimal position, and here we write, since all Zj minus Cj greater equal to 0, so condition of optimality satisfied, and optimal solution is given by x1, this is equal to, here x1 is 4, x2, sorry, this is x2. x2 is given by 0 because here no x2 present, x2 is 0. x3 dash, this is also equal to 0 because x3 dash not present, and x3 double dash, this is equal to 2. Okay, and these are the only original variable. We cannot write slack, surplus and artificial variable in the solution. Okay, with Z max, this is given by 18, right? And we write the final answer as, since this is unrestricted variable, so we have to find the value of x3. Okay, so we get x1, this is equal to 4, x2, this is equal to 0, and x3 this is equal to x3 dash minus x3 double dash, and which is given by this is 0 minus 2, this is minus 2. So the solution of the LPP is this x1 this is equal to 4, x2 this is equal to 0, and x3 this is equal to minus 3, with z max this is equal to 18. Okay, this is the complete solution of the LPP with one variable unrestricted in sign. Thank you for watching.